Hello.
Hello, everyone. I welcome you all to today's session with Dr. Aaronson. He's one of the leading authorities in quantum information, and we intend this to be a question answer session where we have questions from the people, and then we plan to ask you these questions, hoping that you'll provide some insight to each one of these. And It's more or less an informal session. Just we ask people to send their questions, whatever they are. They are most of the questions are very wide and general, so we'll have enough time to address each of these. So I'll I'll get on to the questions shortly.
Okay, great. Hi.
Yes, Professor Aaronson, sorry for the delay. So I would
All right.
like to get on to the first question.
Okay. Sure.
Yeah, so the first question is asked by one of the first year students here. It is,
Okay.
how would you explain quantum computing to a person who has only heard of the term before?
Well, I've been asked to do this many times, even to explain it in one sentence. But the best that I've been able to do is to get it down to about 10 minutes, because I have to start by explaining what is quantum mechanics, right? And that, involves, talking about one of the great, revolutions in human understanding of the universe that happened a century ago. And people often have the impression that quantum mechanics is endlessly complicated, and so something that they can never understand. And I think that it's a great surprise to people when you explain to them that no, the core of quantum mechanics is really just one change to the rules of probability. Okay, it's a different way of calculating the probability that something is going to happen. Okay, and it involves these new kinds of numbers called amplitudes, which are related to probabilities, but they're not probabilities because they can be negative, or indeed complex numbers. Okay, and the central thing that quantum mechanics says about the world is that for every possible way that a physical system could evolve. For example, every path that a particle could take as it travels through a room, you have to assign one of these amplitudes. Okay, and until we make a measurement, the state of the particle, so the most fundamental reality about what is going on with it, is just a list of these amplitudes. It's a vector. Okay, it's one amplitude for every possible configuration. Okay, and then there are two different rules. One for systems that are isolated, and one for what happens when we make a measurement, or more generally when a system interacts with its environment. And when a system is isolated, then this list of amplitudes evolves, changes by means of linear transformations. And when we make a measurement, then we force the system to decide which outcome it wants to be. Okay, and it makes its choice by the famous Born rule, which says that the probability of any outcome is equal to the square of the absolute value of its amplitude. Right? And measurement is a destructive process, right? So once you look, the system snaps to one outcome or the other, and if you look again, then it's still there. Okay, so the basic building block of a quantum computer is what we call a qubit, a quantum bit. Okay, and that is just a bit that has some amplitude to be 0 and some amplitude to be 1. So it's in a superposition of the 0 state and the 1 state. Okay, and just like a classical bit could be physically instantiated in all different ways, as voltage through a transistor, but also as by beads on an abacus, or all sorts of other things. A qubit can also be physically instantiated in many different ways. It could be, the spin state of an atomic nucleus. It could be the energy level of an electron, with the ground state representing zero and the first excited state representing one. Okay, so any physical system that can be maintained in two different states, or as we say, in a superposition of those states, okay, with some amplitude for each. And the key property of these superpositions is that when we calculate the probability that something happens, well, we have to add up potentially many different contributions to its amplitude. And if some of those contributions are positive and others are negative, then the contributions can, as we say, interfere destructively and cancel each other out, so that that outcome would never happen at all. Okay. The classic demonstration of this is the double slit experiment, okay, where you shoot photons one at a time at a screen with two small slits in it. Okay. And then what you find is, well, if I want to know how likely is the photon to end up at a given location, let's say on a second screen behind, I have to add up two contributions to the amplitude. One for if the photon went through the first slit, and one for if the photon went through the second slit. Okay, but in some places, those two contributions will cancel each other out. Okay, meaning that I see like a dark patch on the screen. I see a place where the photon never appears. Okay, and the key demonstration that this is actually what's going on is that if I close one of the slits, so now there's only one way for the photon to go, then the amplitude is only positive or it's only negative. And so now the probability is positive. Right now I can see the photon there. Okay, so to say that again, by decreasing the number of paths that a photon could take to get somewhere, I can increase the chance that it gets there. Okay, that is something that could never happen in conventional probability theory. Okay, but it does happen in quantum mechanics. The way we explain it is with amplitudes, with interference. Okay, so what is a quantum computer? It's a computer that would try to exploit that phenomenon of interference to solve certain specific problems dramatically faster than we know how to solve them with conventional computers. Okay, and how does that work? Well, it's crucial to understand that when I have multiple quantum systems. So let's say, for example, I have two qubits. Okay, the rules of quantum mechanics are unequivocal. That I can't just specify an amplitude or amplitudes for each qubit separately. Rather, I need one amplitude for every possible combination of all the qubits. So, for example, there is an amplitude for both qubits to be zero. Okay, there's an amplitude for the first qubit to be zero and the second one to be one. Okay, there's an amplitude for the string 1, 0 and for the string 1, 1. Okay, so famously, I could have an equal superposition of, let's say, the state 0, 0 and the state 1, 1. Okay, and that would mean that if I measured one of the qubits and I found that it was in the zero state, then immediately I would know that the other qubit was also in the zero state. And likewise for the one state. Okay, this is what we call entanglement. Okay, and it's really just the quantum version of correlation between random variables. Okay, and this continues, right? If I have 3 qubits, now I need 8 amplitudes to represent its state, right? 2 to the 3 power. Okay, one for every 3-bit string. And if I have 1,000 qubits, okay, which could correspond to, let's say, the states of 1,000 electrons, for example, which is not actually very much, right? It's a very small physical system, but quantum mechanics tells me that for that I in general need 2 to the 1,000 power amplitudes. Okay, so I need 1 amplitude for every 1,000-bit string. Now that is far more amplitudes than could fit in the entire observable universe if you had to write them down explicitly. Okay, and yet physics is telling us that when 1,000 particles are interacting, getting into an entangled state, then nature off to the side somewhere has to maintain some scratch paper with 2 to the 1,000 parameters just to keep track of what those particles are doing. And whenever anything happens to the particles, nature has to cross off all of those parameters and replace them with new parameters. Right. So that is a staggering amount of work for nature to be going to, just to keep track of 1,000 particles. And chemists and physicists knew this for generations. They knew it mostly as a practical problem, right? If you are trying to simulate chemistry and physics, with using classical computers, then you face this exponential explosion in the size of the wave function, or in other words, the number of amplitudes that you need to keep track of. Okay, and the physicists have invented all sorts of hacks and approximation methods to try to get around that. Okay, but about 40 years ago, a few physicists, most famously Richard Feynman and David Deutsch, had the remarkable idea that if nature is giving us that computational lemon, then why don't we make lemonade out of it? Right. So why don't we build a computer that itself would operate on these same principles of superposition and entanglement and interference? Of course, they immediately faced the question, well, supposing that you built such a device, which they called a quantum computer, what would it be good for? Okay, and at the time, they were really only able to give one answer to that question, which is it would be good for simulating quantum mechanics itself. Now, as tautological as that sounds, I think that that's still today, the most economically important application of quantum computers that we know about. Okay, but what really started quantum computing as a field, what really put it on most of the world's radar, was the dramatic discovery in the 1990s that a quantum computer can also sometimes be used to solve purely classical problems, ones that have nothing to do with quantum mechanics, much faster than we know how to solve them classically. Okay, and the most famous example of this is Shor's factoring algorithm. Okay, discovered 30 years ago in 1994. Okay, this is an algorithm for factoring an n-digit number, using a quantum computer, using a number of steps that grows only like n squared, roughly. Okay, and recent advances have made it even less than that. Okay, but with a classical computer, the fastest known factoring algorithm takes a number of steps that grows exponentially with n. Okay, or technically with the cube root of n. Okay, so and as some of you might know, the presumed hardness of factoring, and a few closely related problems is the basis for the encryption methods that protect the internet, that the public key encryption schemes, RSA, Diffie-Hellman, elliptic curve cryptography. These are all based on problems in number theory that Shor discovered that a quantum computer would be able to solve efficiently. Okay, so that really made many people interested in quantum computing who hadn't been before. Okay, but there's a very fundamental misconception at this point, right? So after Shor's algorithm was discovered, then people started writing about it in the popular press and so forth, and they started saying, well, the way it would work is that a classical computer would just have to try every possible answer one after the other, right? And there could be astronomically many, but a quantum computer could just try all the possible answers at once. Sometimes they'd say each one in a different parallel universe. Okay, or all of them in superposition, and somehow magically pick the best. Okay, now it's very important to understand that it's not that simple. Okay, if it were that simple, then you wouldn't have needed Peter Shor to think of it. So and here's the catch, right? With a quantum computer, you can create an equal superposition over all answers to your problem, even if there are exponentially many of them, right? That's even an easy thing to do with a quantum computer. Okay, the trouble is that for a computer to be useful, at some point you have to look, you have to measure, you have to get an output, right? And if you just measured an equal superposition over all of the answers, not having done anything else, then the rules of quantum mechanics, the Born rule that I mentioned earlier, tells you that all you're going to see will be a uniformly random answer, right? And if you just wanted a completely random answer, well, you could have just picked one yourself by flipping a coin a bunch of times, right? You didn't need to spend all these billions of dollars to build a quantum computer. Okay, so the only hope of getting an advantage from a quantum computer in solving a problem is to exploit the way that these amplitudes, being complex numbers, work differently from conventional probabilities, right? Again, a probability is a real number from 0 to 1, okay? But an amplitude is a complex number, okay? And the key trick with every algorithm for a quantum computer is that you are trying to choreograph a pattern of interference such that for each wrong answer, that is each answer that you don't want to see, some contributions to its amplitude are positive, let's say, and others are negative. So on the whole, they cancel each other out, right? And leaving a total amplitude of about 0. Okay, whereas for the right answer, the answer you do want, you want all the contributions to its amplitude to be pointing in the same way, to be in phase, to be constructively interfering, right? If you can arrange that, then when you measure, you will see the right answer with a high probability. And of course, you could always repeat the computation, many times to boost the probability even further. Okay, but the whole quantum advantage comes from using interference to boost the probability of the right answer to be much more than it would have been by just classical random guessing. Okay, and what Peter Shor showed 30 years ago was how to choreograph that interference pattern for the very specific problem of factoring a number. Okay, and to do that, he had to take advantage of very, very special properties of the factoring problem coming from group theory and number theory. Okay, and so he had to figure out how to concentrate all the amplitude on the right answer, the answer that reveals the prime factors, even though you yourself don't know in advance which answer is the right one, right? If you already knew what would be the point, and you have to do all of this fast, or at least faster than the fastest known classical algorithm can do the same thing. Since again, otherwise, what would be the point? Okay. Since then, in the 30 years since, there have been many other important quantum algorithms that have been discovered, such as Grover's algorithm for searching, which we could get into later. There's also been lots of exciting progress on how do we actually build a quantum computer at scale. Okay, but that's the basic answer as to what a quantum computer is. So was that about, I don't know, 10 minutes, 15 minutes? That's that's about the shortest answer that I've been able to devise.
It was indeed a very interesting answer. Given that most of the audience is freshmen and sophomores, I'm sure this was very informative for all of us. Okay, so the next question we have is from Aran, a fourth-year student. What he's asking is, we can see that AI has kind of taken over the world in many aspects. Maybe maybe in doing tasks or whatever. So is the we are what he's asking is, what are the implications of this? Is this a good thing or a bad thing? What can we think of this in general?
Oh, it's what was it there that who was it, that historian who was asked, like, was the French Revolution good or bad, and he said it's too early to tell, right? It's this is such an enormous question, right? It's I do expect that AI is going to transform just about every aspect of human existence, in this in our lifetimes. I think that as long as AI just sort of, remained a tool that did certain things for us better, but there were still things that you needed humans to do or that only humans could do. Then it is similar to, or can be understood by analogy with many previous waves of technological innovation, right? I mean, the car, caused many problems, right? It put horse and buggy drivers out of work. It caused accidents. It led to more, social isolation, right? But we probably don't want to go back to the world before we had it, right? Likewise for the printing press, likewise for the internet, right? And we can go on and on with examples of technologies, right? I mean, I feel like on the whole, civilization, technology, these have they've caused many problems, but I personally would not wish to go back to the world before we had these things, right? And so if, as long as AI just sort of remains a tool that let's say helps us with our writing, or with as a personal assistant, let's say that it seems very predictable at this point that, like, within a decade, the way that we will interact with our computers will just be, the way in Star Trek, right? You just tell your computer in words, what you want it to do, you know, and it goes and it does that thing, right? I mean, probably existing large language models, GPT-4 and Claude and so forth, might already be capable of that if they were, better integrated with all of our existing, with all of our other software tools, and that's probably coming in a matter of years. And Microsoft and Google and other companies are racing to make that a reality. Okay, so if let's say we had that, we had robots to do our laundry, do our dishes, fold the laundry, do all that stuff, right? That all seems good in the same way that previous waves of innovation were good. Now, where the question becomes harder is when you ask, well, what if AI reaches a point where it can do everything that a human can do better than the human can, right? Then what are we still even there for, right? I mean, you could say in that scenario, the best outcome is just that we get to kick back, enjoy our lives, with robot butlers, servicing our every need. We're not ourselves really needed for anything, but we can essentially spend our whole lives just pursuing enjoyment. If we want to solve difficult problems, the AI can give us problems that are right at the perfect level of difficulty for us, and of course the AI could have solved those problems better, but it can give us challenges to keep us occupied. That's the sort of good outcome, right? Where we are either some people would say that we're like emperors in that world, other people would say that we're like pets. Okay. And then the bad outcome is that the AI is not aligned with our goals. It has its own goals, and it decides that we're not actually needed anymore, and it just gets rid of us, or it puts us or even if it keeps us around, we sort of lose control over the future. It puts us in a world that we really don't like. And so I think that these are enormous questions, and I'm not a very good prognosticator. Like I did not foresee that large language models would become as good as they did, as quickly as they did. So if I couldn't even predict 10 years ago what was going to happen now, then far less can I predict what's going to happen in the rest of this century. But I do think that we can see problems like right in front of us. We can see the AI that already exists is already being misused. For most obviously, where millions of students are using language models to cheat on their homework. I'm sure none of you have ever done that, but one reads about it. And people are also using it for deep fakes, for propaganda. They're very soon, I expect them to be using it to help with hacking into servers, and controlling important infrastructure, things like that. You could imagine people using AI to help them build chemical weapons or biological weapons. Okay, these are all things that we can see right in front of us. And so I've actually despite spending most of my career doing quantum computing, just as some context, I've been on leave for the past 2 years, working at OpenAI, trying to think about what can theoretical computer science do for AI safety. And I still don't have a really good answer to that question, but I've broken off little bits and pieces that where I think theory can make progress. And I think what is exciting about this the current time is that we actually can make some progress on AI safety, on making things go well, because we now finally have these very powerful AIs that are being deployed in the world, and so we can try different methods to align them or control them, and we can see what works and what doesn't. So even if we don't know how AI is going to transform civilization, we can at least see as far ahead as we can, and that far we can try to steer things so that we are happier with the outcome. Yeah, I'm happy to take other questions.
Oh yeah, just 1 second.
Sure.
Yeah, hello. Yeah, I'm from here. I'm a PhD student.
I can't really hear you.
Hello, can you hear me now?
Yeah.
Yep. I'm from here. I'm a PhD student here.
Okay. Can you speak louder and clearer? Yeah, there's a lot of feedback.
Yeah, just give me 1 second.
Okay, maybe you could type your question in the chat window. Hmm?
Oh, can you see on screen? That's it.
Hello.
Yes. Hi. Now I can hear.
Awesome. I'll take it over here. So I'm a 4th year student here at ISER, and yeah, but that was a really brilliant answer. Thanks a lot. I mean, like, it's a very general question, I understand. I mean, it's been going on for quite a while. But one of a specialized question from there was by the student was, I mean, like, what means to be creative, and what does it mean to have certain problems that AI itself is not able to tackle? Perhaps you can shed some light on that. And maybe, I mean, like, since you're into quantum computing, you have this idea of QML, right? Quantum machine learning, and what's going on there. So maybe these are certain questions.
Okay, so there were a bunch of different questions there. what does it mean to be creative? So that's a hard question. I mean, usually we call something creative, if it's not just sort of doing the obvious thing at each step, right? Like, let's say a mathematical proof, that's what I can speak about more competently than art or music, probably. But usually a mathematical proof would be called creative if it involves some new object or construction that was not mentioned in the problem statement, and which seems to come out of left field, right? Like maybe you have a problem just about positive integers, but suddenly you start talking about complex numbers in the proof, or about elliptic curves, or modular forms, or some crazy other thing. Okay, and only by the end do you see why this out of left field thing was actually the key to the proof. So when, like, under what circumstances should we say that an AI is creative, right? Well, I mean, like, maybe a simple answer, the answer that Alan Turing gave 3/4 of a century ago, was that let's just regard an AI as creative if it produces an output that we would have called creative if a human had produced it, right? So if we can interact with the AI, we can submit challenges to it, and then it gives us solutions to those challenges, and we cannot tell its solutions apart from those of a very creative human. Then it seems like if we're going to call that human creative, then we ought to call the AI creative as well, right? Or at least, if we don't, then the burden is now on us to explain why not, right? Is this just discrimination? Is this, anti-AI racism, essentially, right? Why should we call the same product creative if a human produces it, but not if an AI does, right? And I think a lot of people would say, well, the difference is we know how the AI works, right? We know that inside it's just doing search, it's just doing gradient descent on these parameters of a neural network. It's just twiddling bits around, right? The trouble is that a scientific reductionist would say exactly the same things about humans, right? We are just a collection of neurons and synapses that are acting according to the laws of physics, right? We are just a bundle of neural firings and so forth. And so if you're too reductionist, then you can make it look like nothing is ever creative, that there's no creativity anywhere. So but if we're going to say that there's creativity in our case, then it seems like maybe we should also have to say that there is or could be in the case of AI. Okay, and this is not to say to render a judgment about whether the outputs of the specific systems that exist now, like GPT or DALL-E, are very creative. Some people might say that they're creative at a sort of lower level, a level of sort of writing clever poems, making striking artworks, but maybe not yet creative as judged at the very highest level of sort of creating a whole new form of poetry or a new form of artwork. Now, if that is where the bar now is, then it's very important to remember that that's a bar that most humans don't clear either, right? Most humans go through their whole lives without ever creating a new literary form, or a new mathematical proof technique, or anything that enormous, right? It's only maybe the most creative and celebrated humans ever who do those sorts of things. Okay, but you could say, okay, fine, that is a bar that AI has not yet cleared. Now, I remember there was another question about quantum machine learning. Once people understood about quantum computing and its potential to speed up, certain specific problems like simulating quantum mechanics or like factoring huge numbers, then people got very excited that a quantum computer is just the universal way to speed up everything, right? It's just going to solve every problem in optimization and finance and AI and machine learning, much faster than classical. And and this is a vision that's been now sold to investors and government funding agencies, and by and large, they've just eaten it up with mustard, right? And the problem is that that is not consistent with our understanding of quantum algorithms. So what I'd say is that for these again, to get an exponential speed up for the problem of factoring numbers, Shor had to exploit this very carefully choreographed interference pattern, right, that takes advantage of very special structure in the factoring problem. Now, for more general problems involving, let's say searching, a huge space of possible parameter settings, which would encompass a large fraction of what we want to do in AI and machine learning, for example. The best quantum speed up that we know tends to come from what is called Grover's algorithm. Okay, so Grover's algorithm is maybe the second most important quantum algorithm after Shor's. It was discovered by Love Grover in 1996. And what it does is it can take any list of n possible solutions to a problem where you know how to check any given solution to see if it's correct, and it can find you a correct solution if there is one, using a number of steps that scales only with the square root of it. Okay, so whereas classical brute force search would require a linear in n, a number of probes until it's like looking for a needle in a haystack, right? So compared to Shor's algorithm, Grover's algorithm has an enormously wider range of application, right? Like if you just look through an algorithm's textbook, probably three quarters of what's there, has some component that can be Groverized. There is some for loop, for I equals 1 to n, where you check possibility I and see if it is correct, right? And any for loop like that can sort of be replaced by a Grover search that will only take square root of n steps. Okay, so that's the advantage, enormous generality, including to problems in AI and machine learning. The disadvantage is that Grover's algorithm is not an exponential speedup. It is only, quote unquote, a square root or a quadratic speedup, right? And so, the square root of 10 to the 20 is 10 to the 10. So that's indeed better, right? But the square root of 10 to the 2000 is 10 to the 1000, right? Still an extremely large number. Okay, we haven't really gotten into the practical issues of building quantum computers, but suffice it to say that to run to build a scalable quantum computer, you're going to need something called quantum error correction, okay, which is just starting like within the past year to be demonstrated in the lab. Okay, and as far as we know today, running quantum error correction would incur an enormous overhead, like a huge constant factor overhead, let's say of a factor of 1,000,000 or something like that, right? And so now the question is not just n versus square root of n, right? The question is, n for the classical computer versus 1,000,000 times square root of n for the quantum computer, right? And how large does n have to be before 1,000,000 times square root of n is less than n? Well, the answer is n has to be like a trillion, right? So Probably in practice, Grover's algorithm only becomes a net win over a classical computer when you get to quite enormous problems. And so that's probably not in the near future. Like even after we have scalable quantum computers that can break RSA, we might still not be seeing an advantage from Grover's algorithm, right? And so then the question is, if we leave out Grover's algorithm, then how else could a quantum computer help with ML and with AI? And so now there's been, at this point, I would say 25 years of speculative ideas about how else a quantum computer could potentially help us with ML and AI. There are some very intriguing ideas. There are some like heuristic algorithms that we don't really understand their performance, but maybe they give a speed up over a classical computer for some practical AI problems, conceivably even an exponential speed up sometimes, but we don't actually know, right? We might not know until we can test these things out on actual quantum computers and find out empirically. So I think it tends to be like the speed ups that we're confident about for AI and ML, the quantum speed ups, I mean, tend to be modest, like Grover like, and the ones that are really huge and game changing, like exponential, tend to be ones that we're not confident about, or alternatively, we're confident about them, but they're only for extremely artificial special cases of the AI and ML problems. For example, if you contrived a machine learning problem that involved factoring a huge number, well, then of course a quantum computer can give you an exponential speed up, right? But that's not most machine learning problems. So I regard, the question like, is there a huge speed up? Is there a huge quantum speed up for machine learning or AI that will really matter in practice? That is an open question. That's a research question, and it's a very important, profound question, and lots of people should be working on it. And I'm glad that they are. But we should also be honest about where our knowledge currently is, and not hype things up and lead people to believe a false vision about it.
Yep, that sounds fair. I mean, given the fact that these problems are that niched, I mean, like you really don't know where exactly you find a general usage of them. But yeah, thanks a lot for your answer. That's pretty elaborate.
Sure.
Thanks a lot.
Sure.
Yeah, so you did mention practical applications. I mean, like coming to practical quantum computing. I think that's where we go to our next question from Asaf.
Okay.
So he's talking about quantum memory and storage, and essentially, I think he wants to know how practically we have a quantum computer. Especially, you were talking about the recent years' work on quantum computing with NISQ. I mean, that was a neutral atom-based from Lucan's group. So and you have superconducting circuits with IBM. I mean, like, what are your thoughts?
Yeah.
Maybe you can start with this.
Sure. Okay, so
Yep.
to start with, the advantages of a quantum computer over a classical one, are not really in memory or storage, right? If I want to store n classical bits, there's a very famous theorem called Halevo's theorem that says that I can't actually do it with much fewer than n qubits. That is, if I later want to measure the qubits and retrieve the classical bits reliably, right? But it is a very important problem, to figure out how do we store qubits. And you could say, the problem of building a reliable quantum computer, let's say, at least like more than half of that problem is just how do I keep even one qubit alive for an arbitrary length of time, right? How do I get it to maintain its quantum state arbitrarily far into the future? Okay, now the fundamental difficulty with actually building a quantum computer, I alluded to it earlier when I said, if measurement in quantum mechanics is a destructive process, right? If I look at a qubit, I force it to decide whether it wants to be a 0 or a 1, for example. Okay, but crucially, it doesn't have to be a person who is looking. Any sort of interaction between the qubit and its external environment, like the radiation or the air in the room, that carries away information about whether that qubit was a 0 or a 1, will have the same effect on the qubit as if someone measured it. Right. So it will destroy its quantum state. Right. And so what this means is that, if you want to build a scalable quantum computer, you have to keep the qubits incredibly well isolated from everything else in the universe. Right. You have to, keep them almost perfectly isolated from their environment. At the same time, they can't be perfectly isolated because something has to come in and tell the qubits what to do, make them interact with each other in this precisely choreographed way. Okay, so those twin requirements are so staggering that, after Shor's algorithm was discovered 30 years ago, there were distinguished physicists and computer scientists who said, this is fundamentally impossible. You will never build a large quantum computer. Maybe you'll build a tiny one, but you will never be able to control quantum states to the degree of accuracy being talked about. And they bolstered their argument by pointing out that amplitudes are continuous quantities, right? And there's a reason why analog computing, never really took off in the 50s and 60s, right? It was because if I have an analog device, then the smallest error can snowball over time, right? And just completely destroy my computation. This is why we use digital computers instead, right? And a transistor, does this magical thing that it sort of it does logical operations on voltages that are in basically a discrete state, right? They're either there or they're not there. Okay, so now what changed almost everyone's views was another crucial discovery in the mid-1990s, and this was the theory of quantum error correction. Okay, and Peter Shor again played a crucial role in discovering this. Many other people were involved as well. And the upshot of this theory was that if you want to build a reliable quantum computer, you don't actually need to get the qubits to perfectly isolated from their environment, nor do you need to operate on them perfectly. Right? You merely need to get them very, very well isolated, and operate on them very, very close to perfectly. Okay, and once you've passed some finite threshold, in the accuracy with which you can isolate and manipulate qubits, then there are these very clever quantum generalizations of error correcting codes that can get you the rest of the way. Right. So, an error correcting code is something like, the simplest example would be I encode 0 by the 3 bits 0, 0, 0, and I encode 1 by the 3 bits 1, 1, 1. Right. That's the 3-bit repetition code. And then if any one of the 3 bits were to be flipped, then I can both detect the error. Right. I see that the bits are not all the same, which means an error must have happened. And I can also correct the error by changing the wayward bit to back to the majority answer. Okay, now and error correction, of course, plays a central role in classical communications. It was pioneered by Claude Shannon 75 years ago. But people said, well, error correction is never going to work for quantum computers because, error correction involves constantly looking at your bits to see whether an error has happened, right? But if I constantly look at qubits, well, that's going to destroy their state. So how can I do that? Okay, and the remarkable discovery people made is that it's possible to design quantum error correcting codes where I only make measurements that tell me has an error happened, and if so, what do I need to do to fix it, right? And they don't tell me more than that. They don't tell me, is this qubit a 0, or was this qubit supposed to be a 0 or a 1? I don't want to learn that, because if I did learn it, then I would have collapsed that qubit, right? So and then this discovery of quantum error correction, within a year or two, it was generalized to a full theory of what we call fault tolerant quantum computation. And basically, this theory explained in principle how you could build a reliable quantum computer even out of unreliable components. Okay, and it said, even if every operation that you're doing on every qubit or every pair of qubits is failing at some constant rate, then as long as that rate is small enough, like let's say 1 in a million, okay, then you might think that if every operation fails, with 1 in a million chance, then I can only do a million operations until probably some step will have failed. Okay, but no, once I get my error low enough, the theorem says that then these error correcting codes get me the rest of the way. Okay, I can correct the errors faster than my error correction is introducing new errors, and I can thereby push the effective rate of error arbitrarily far down, as close to 0 as I would like. Okay, and I can do as long of a quantum computation as I'd like on as many qubits as I'd like. Okay, so at that point, my qubits are behaving, as if they were just theoretically ideal qubits. Okay, so that discovery of quantum fault tolerance is what sort of has set the engineering agenda of quantum computing for almost 30 years now, right? The goal since then has been to get control over qubits, doesn't have to be perfect, but is just good enough that these error correcting codes can then get us the rest of the way, and you could then scale up to a system with as many qubits and operations as you wanted, and you could keep the qubits alive, keep them in their superposition state for as long as you needed them there. And we're not there yet, but we are much closer than we were. Let's say in the 1990s, right? So when I started in quantum computing, which would have been in the late 90s, I was actually a summer student of Lav Grover at Bell Labs, and then became a graduate student of Umesh Vazirani at Berkeley, who was another of the pioneers of quantum computation. And when I started in the field, like, it would have been amazing if you could do a 2-qubit gate, so like an operation to entangle 2 qubits with 50% accuracy. Like that would be a Science or Nature paper, okay? But a decade later, that 50% had become 90% maybe, and then 95%, and then 99%. And then 5 years ago, many of you may have seen that Google reported this quantum supremacy demonstration, so they built a system with 53 superconducting qubits. And this was building on an earlier proposal by me and my student Alex Arkhipov for how to demonstrate a quantum advantage. Admittedly, not a quantum advantage for any useful problem, but a quantum advantage for some artificial benchmark task, right? And so they did this by just taking building a chip with 53 programmable qubits, and then applying a random sequence of 2-qubit operations to them. Okay, they did about 1,000 operations, and then they measure, and they see a distribution over 53-bit strings, and and then they argue that seems challenging to sample with to sample from the same distribution using a classical computer. Okay, and they were not using any error correction here. They were just eking out an advantage, even in the absence of error correction. But what they found was that the errors on the qubits, were more or less independent. Which, as long as that remains true, then the crucial assumption in the theory of quantum error correction seems to be satisfied. So in the Google experiment, this is again 5 years ago, there, each gate had about 99.5% accuracy, right? So, and now since then, it's gotten better. And within the last year, what we've seen, especially in other hardware architectures like neutral atoms, which Quera in Boston has been doing, or trapped ions, which Quantinuum in Colorado has been doing. They're demonstrating 2-qubit gates with 99.9% accuracy. Okay, now how accurate do we need? Well, on paper, the best fault tolerance schemes that we currently know start to work once you have 2-qubit gates with 99.99% accuracy. Okay, so 4 nines instead of 3. Okay, so it looks like, if you look on that metric, if you just plot the errors on a log scale or something as a function of what year it is, then you feel pretty optimistic about this, right? It feels like the engineers are well over half of the way there now, and that they ought to be able to get 4 nines, and then quantum fault tolerance ought to work. And indeed, within the last year, what we've seen is from Quera, from Quantinuum, and from Google is, in different ways, like the first uses of quantum error correcting codes to get some sort of advantage, some very, very small advantage compared to not using quantum error correction. Now this was for very limited tasks. It's not yet full quantum fault tolerance. Okay, but we've finally seen, the predictions of the theory of quantum error correction tested experimentally within the last year. So it's an exciting time. So it looks like maybe people have to go at this point. Or...
I'm not sure. I guess people are pretty hooked up. I mean, that's
all
why.
Right. Well, maybe I could do like one more question.
Yep. I mean, like the one last question was actually
okay,
something.
One last question. Yeah, perfect.
Yep. So, I mean, like one of the questions was about talking about the milestones that we'll be reaching in quantum computing in the future. I think you sort of did touch upon it
yes.
based on the fact that we are reaching a certain level of fault tolerance and infidelities in our gates and operations. So, I mean, this is something that I think a lot of my friends and people are asking. The QC bubble, I mean, like it seems to be hyped. To a certain extent. So is the hype real? I mean, like you did give quite a lot of evidence to it. So what do you feel?
Yeah,
I think we'll end on that.
I mean, you sort of have to drill down with that sort of question to a higher level of granularity, right? It's like there's certainly a lot of hype around the question of what is a quantum computer going to be good for, right? People want it to be, a much more broadly applicable than it is, I think, or than the evidence supports. They want it to just be, the next general revolution in computing, right? So we would all have a home quantum computer, right? And the trouble is, for most of what we do with our computers, classical computers are already perfectly good enough, right? And to the extent that they aren't, it's not for any reason that a quantum computer could obviously fix, right? most algorithms, that our computers would use on a day-to-day basis are ones that only admit a modest quantum speed up, so such as a Grover type speed up, as far as we know. Okay, so quantum computer really does seem to be like a special purpose accelerator for breaking public key encryption, for better or for worse, for simulating physics and chemistry, which could have lots of uses, designing new batteries, new solar cells, new drugs. These are maybe not things that most of us do, but we could all benefit from the people who are doing those things. And then maybe some other uses, maybe eventually Grover's algorithm becomes useful, for example. But the other uses are kind of more speculative. I like to say that for me personally, the number one use of a quantum computer from the very beginning has always been just to disprove all of the people who said a quantum computer is impossible. Or in other words, it's to test quantum mechanics itself, in the most severe way that we're ever going to see it tested. And to me, even if there had been no other applications besides this one, this would still be worth doing. This would be, for the same reason why, our world spent, $10 billion to build the James Webb Space Telescope, right? Or, more than that, to build the Large Hadron Collider, right? And, these are, things that just peel back the curtain of the universe a little bit further. And I think that testing that there really is this exponential computational power in nature beneath the surface, that would, to me, that would be the same kind of thing. What I've seen again and again is that when people realize that the applications of quantum computers to machine learning or to AI have been wildly overhyped, right? And once they realize that, they often then do an extreme overcorrection in the opposite direction. Okay, then they say, oh, well, then the whole field of quantum computing must be a sham. Like quantum computers must just be impossible. And in fact, these people talking about it, like who knows if quantum physics is even right, right? Or if we, if the rules really work that way. Okay, but then at that point, the ball is really in the skeptic's court, right? And I would say that if a quantum computer turns out to be impossible for some deep reason, then that is much more surprising and interesting and exciting than if a quantum computer is possible, right? Because for it to not be possible, especially after the discovery of quantum error correction, right? For it to not be possible would really require something to break in our current understanding of quantum mechanics itself. Okay, and that would be a revolution in physics. And any of us who work on this would be thrilled to be part of that revolution and to collect the Nobel Prizes, right? It's like the mere success in building a quantum computer would be like the more boring outcome, the more conservative outcome in comparison to that. Okay, but so my expectation is that yes, this will ultimately be possible, if people want it badly enough. Of course, it's always like with any technology, fusion power or space elevators or flying cars or whatever, it's always possible that it will just be too expensive and people will give up or the funding will run out or things like that. But I think if people want this badly enough, then yes, everything we've seen tells us that ultimately this is possible. And yes, it should have at least some applications, if nothing else, to simulating quantum mechanics and to breaking public key encryption. And to helping us understand or test quantum mechanics itself in a whole new regime. So I feel like that is an honest case for quantum computing. That's a case that I can make and then sleep perfectly soundly at night. There is also a dishonest and hype-filled case that you can make, but hopefully you won't hear me making that case.
Yep. I mean, Thanks a lot for the answer.
Sure.
I think
Yeah.
we'll
All
just
right.
take
So
a few pop. Oh, you should be you out of time. If it'd be possible to take some questions from the people here, maybe just one. I'm sorry if I'm taking too much of your time.
Oh, it's all right. Okay. Well, I'm one. Well, I'm one more then. But also I don't want to keep people here for too long. But let's do one more then.
Sure. I think Prithvi had raised his hand first. So
Okay.
maybe you can take it over. Prithvi, are you there?
Unmuted.
Hello, can you hear me, sir?
Yes.
So I had a question, a general question and a more specific question. But my general question is whether the brain itself is a quantum computer, and are there analogs of a Turing test or like a quantum Turing test to say whether something is a quantum computer or it isn't?
Well, okay.
And
So
my specific question was you talked a little bit about QML. And
Yeah.
why is it so hard to quantize the perceptron itself? Is it because you rely on binary thresholds for activation, or like is there something more wrong with
Okay. All right.
quantizing a classical regime?
All right, so there were several different questions there. So is the brain a quantum computer? I mean, you could say that every physical system in the universe, in some trivial sense, is a quantum computer that computes its own time evolution, right? In other words, it computes its own behavior. I mean, as far as we know, quantum mechanics is a universal theory, that applies to everything in existence. If you go down to a small enough scale, everything is quantum mechanical. Okay, but in practice, we often are able to treat systems as classical, right? There's a reason why it took until a century ago for anyone to even realize that quantum mechanics was the fundamental truth of nature, right? And that the basic reason for that is this loss of quantum coherence, right? As quantum systems interact with each other, it's as if they are constantly measuring each other and sort of forcing each other to act like classical systems. Sort of this is the usual story about how the classical world of our experience emerges from the underlying quantum reality, right? And this is why we don't see Schrodinger cats, on the scale of everyday life, right? Because if there were such a cat, then it would only survive for a tiny, tiny fraction of a second before, interaction with its environment had forced it, either to the alive state or to the dead state. Okay, and so I think what conventional neuroscience would say is that very much the same thing is true of the human brain. That is, if you go all the way down to the biochemical level, then yes, you have these molecules that have to be described by a wave function. Chemistry, only works because of quantum mechanics, right? And even if I ask, like, does a particular sodium ion channel open or close? It's like, does a particular neuron fire or not fire, right? That could be a chaotic event, right? Which is ultimately, pushed in one direction or the other by some, amplified quantum mechanical event, right? So that, like, even if you had all of the information about someone's brain that it is physically possible to know, you still might not know, what decision they're going to make or what they're going to say next, because it might depend on some, some sort of a chaotic amplification where, like, first there is some molecule, that's in some quantum state that gets, that gets decohered, and then that causes one neuron to fire, and then that neuron causes a cascade of other neurons to fire, and before you know it, the person has made a different decision, right? Just like with the butterfly effect, right? The reason why the weather is not predictable beyond a certain point, right? And you could ultimately trace your uncertainty all the way back down to your uncertainty about the quantum states of the molecules in the neurons. Okay, but despite all of that, we might still not want to describe the brain as a quantum computer. Okay, and the reason is that once a neuron has either fired or not fired, then that seems like a classical event, right? That seems like something that you could make an external record of without really changing what has happened, right? Because at that point we're at like well, compared to the scale of atoms, we're at almost a macroscopic scale, right? We're at sort of enormous, and slow and hot systems.